Thank you. Hi, everyone. My name is Robert. I'm a PhD student at UC Santa Barbara. I'm here to talk to you about our dynamic analysis system to detect regular expression denial of service vulnerabilities. So let's get started. I want to warm everybody up by just thinking about that code review that you just got on your desk, right? So you've got a patch to review, and you want to give the thumbs up or thumbs down on it. You get it in, and yeah, it looks a little scary. There's a regular expression in there, and we all know they're hard to read. So squint at it a little bit, and but it comes with unit tests, which is great, and they all seem to pass. And this seems to sort of meet your general expectations for what might have to happen here. So you give it the thumbs up, of course. Actually, unfortunately, this is a vulnerability. In fact, we identified it during the course of this investigation. The problem here is that this regular expression, of course, executes in polynomial time, worst case. If an attacker could control that input parameter URL string, then it can cause excess CPU usage on the victim machine when this is running. But don't worry, you're in good company. Last we checked on this package, they had 26 million weekly downloads. We find this issue all across the ecosystem, and prior work has found it everywhere as well. Backing up a little bit, so what is ReDoS? Just to remind ourselves, it's a type of denial of service attack. This type of denial of service attack is a little bit more advanced than just pushing through a ton of traffic. The idea here is that the attacker is attempting to achieve asymmetry by finding a method of making it amplify the amount of damage that they're doing with very little effort. And of course, complexity in victim software is exactly one of these methods of amplifying the attack. Regular expressions, it turns out, are exactly a type of software where we have this type of hidden complexity, which is difficult to identify but easy to exploit if you are an attacker. We know that it has significant real-world impact. At USENIX a few years ago, we had a presentation showing that hundreds of popular websites are vulnerable to at least one ReDoS vulnerability, so it is a serious problem that's out there. And prior results have been good, but incremental. We note that each time we compare against prior tools, there's a high false negative rate and high false positive rate. In fact, we saw in the first presentation here that comparing against ReDoS detection tools for backtracking matchers, even for a tool not intended for backtracking matchers, can be, show quite improvements. So we really have to question whether we were finding everything here. Moreover, all of these previous methods have severe limitations on the feature sets. So as regular expression engines evolve into the future and more features are added, the analyses really need a little bit more thought put into them. I can't go over exactly what these prior tools were doing, but just to give a general intuition, let's think this through a little bit. So ignore the fact that back references exist for now, and let's imagine that modern regexp matching engines only match against regular languages. We know from our good CS1, 101 classes that these are all represented by a non-deterministic finite automaton. But of course, we're running on deterministic hardware. So how do you do the matching? Well, you need to do a depth-first search from the starting state, which is constrained by your input string you're matching against, and see if you can end up at an accepting state. I show here an example of an ambiguous automaton. And the problem, as we can see here, is that imagine that you've managed to reach state Q2 by consuming perhaps an A and then a B. You now have to make a decision as to whether to go to state Q1 or back to Q2 when you're consuming the next B. Of course, if an attacker knows that you must make this decision, they can exploit that fact and make you constantly guess the incorrect location. And then in a backtracking matcher, you'll have to backtrack to try the other decision point and so on, and it will blow up in this manner. Generally speaking, these prior diagnostic attempts are attempting to look for these types of ambiguities and pattern syntaxes. But in fact, this actually isn't how modern regular expression engines really operate, or at least not the backtracking ones. It turns out that they are a full software system that's embedded within modern languages. When you go and run a regular expression, there's a full lexer and parser and a compiler that will go emit bytecode. When you run the matching procedure, this bytecode actually runs on a lightweight interpreter, and the output of that interpreter will give you an answer as to whether there's a match or no match, and if it did match, any matching groups that were captured in the process. This, if you're wondering, is also called Spencer's backtracking algorithm, so it's pretty well documented. It's been known in the literature for quite a while. So we need a new approach for detecting ReDoS, and we need to make sure that it puts this front and center, and this is exactly what we do. We fully embrace the idea that regular expressions are software in and of themselves, and we embrace the complexity that it comes with. We don't try to hide from all of the advanced features that are existing in modern regular expression engines, and instead we use the tried and true software testing tools that I think everybody here might know. What we do is we invent Regulator, which is a surprisingly simple solution, which achieves very good results for exactly what we want to do. We start by using a slowdown fuzzer, which is a specially modified fuzzer, which, given an input regular expression, will try to find examples of strings that will be very slow when they execute. Then we take examples from this fuzzer, and we derive a formula that will show us how attack strings are formed for this particular regular expression. And then we dynamically verify that this, in fact, is an example of a ReDoS vulnerable regular expression. I'll talk about each of these in turn, but I'll start with the fuzzer. This probably looks very similar to everybody who's seen a feedback fuzzing system. I'm going to talk about a small amount in these particular components, and for more details, of course, please read our paper. For one, we instrument the execution engine regexp. This is the regular expression engine that is found in Firefox, Chrome, and Node.js, so has fairly widespread use. In order to track execution and get feedback, we instrument the interpreter, and we use an AFL-style perf map to collect coverage. This is effectively an array of cells where each cell will count the hit count of branches that occur in the bytecode as it's running. Then, of course, we're trying to fuzz in a different way than you've seen in traditional fuzzers. Traditionally, we're trying to look for something like crashes or bugs, but instead what we're looking to do is find slow inputs. So we want to find the longest path inputs while also avoiding local maxima. And the way we do this is by doing a smart prioritization system. Each time we run the prioritization procedure, we will go and we will find a representative from each of the components, which will maximize that component when it runs. And we prioritize those maximizing representatives. However, there's a problem with this. Of course, the entry point component is extremely boring. Every single string will execute it, probably execute it exactly once, so they're all maximizing, and then you'll waste time. So we also have a deprioritization method, where if an input is found to be stale, that is, if it's not producing novel mutated offspring, then we will deprioritize it and look elsewhere. For the mutation engine, we also have another interesting mutation. We call it suggestion. Because the interpreter is so simple, most of the branches that are taken are actually based on a character comparison within the string that we're examining. So during the execution, whenever we take a branch, we will actually note what character should have been at what position in the string in order to negate the branch condition. Then, during mutation, we will randomly go and change out that character to hopefully negate that branch and uncover more interesting functionality. That's information about our fuzzer. So now moving on to the formula derivation procedure. We take the single slowest string that our fuzzer identified, and we call it the witness. Now, this witness represents just a single point on a complexity curve, so we actually don't really know how bad this is yet. It could be a linear complexity curve, which is OK. It could be polynomial, which is bad, or it could be exponential, which is very bad. So what we do here is we attempt to find a formula which will describe both how to build attack strings and then also let us measure the complexity curve. We take inspiration from prior work, and we say that a formula consists of an attack prefix, some pump string that is repeated, and then an attack suffix. From here, we actually just perform a heuristic scan over the witness string that we extracted from the fuzzer, and we try to find a pump string which, when repeated, causes significant slowness. Once we find that pump string, we sample several different points, and we use a model fitting procedure to figure out which of the three curves I mentioned before it best describes. We take the output from that formula derivation procedure, and then we feed it into our dynamic verifier. Here, the entire goal is just to make sure that this is in fact an example of ReDoS. And what we do is we immediately find the longest Attac string, which is under 1 million characters, and we see if it causes 10 seconds of delay when we're executing it. If it is, then we label it as a ReDoS vulnerable regular expression, and we will binary search for the slowest possible string that causes 10 seconds of slowdown. 10 seconds and 1 million characters is just values we found in the literature, so we reuse them and they seem to work well for the description. We evaluate against several prior tools, in fact, the tools that we saw in the first presentation. We also compare by replacing our slowdown fuzzer by a generic off-the-shelf algorithmic complexity fuzzer called perfuzz. But for more details on that, please check out our paper. For the data sets, we use 3 standard corpuses of regular expressions, and we also scrape NPM, and we find 40,000 regular expressions from that scrape. The first question we have is, well, we built this fuzzer custom, so does it really work? And so we collect coverage as we fuzz, and this graph shows how that coverage evolves over time. I want to point out the fact that the x-axis here is in a linear scale because the coverage actually increases so quickly, so we sort of need to change it to see the detail here. It turns out that even for large regular expressions, we get quite good coverage within 10 seconds and excellent coverage within 100 seconds. So we think that the fuzzer is properly exploring the program. How does it compare in terms of detections? This is a giant grid of numbers, so I'm just going to focus your attention down in the bottom right. We find that our true positive rate is much, much better, in fact, 2 to 7 times better than prior tools, and our false negative rate is quite low. We also find the same for our NPM data set. We also find several novel detections, so we were assigned 6 CVE numbers when reporting vulnerabilities in this investigation. We verified and fixed dozens of bugs. And the positives that we found contain several difficult to find detections, including regular expression denial of service attack, regular expressions vulnerable to ReDoS, which require certain flags to be set in order for the ReDoS vulnerability to present, which of course we support natively because we're just running on the bytecode. There's also several detections where the regular expression itself is highly complex, and so it sort of trips up other static analysis attempts. And also, we find some that use advanced features like back references, lookarounds, and special character groups. Just to wrap things up, a quick recommendation. We find when we're looking for the shortest string that triggers ReDoS, if you wanted to mitigate almost all of the ReDoS vulnerabilities that we found, you probably want to limit your input strings to maybe 1,000 or 10,000 characters, and then 10 seconds of delay would be impossible in almost all of the vulnerabilities we found. So that seems like a good recommendation. Just as a reminder, here's a diagram of our system. Our artifacts are available, so please go check them out. And thank you, everybody, for attending my talk. I'll take questions.